Just like to say thank you for the research grant in the first instance, and also thank you for allowing me to present some of my preliminary data here today. So as part of a background to the rationale behind the study, it's part of my PhD thesis looking at voluntary fluid intake in response to different exercise in different environmental conditions, and also following different bouts of exercise. So today, looking at the effect of high intensity intermittent exercise compared to continuous exercise on voluntary fluid ingestion. So following a period of exercise, replacement of fluid is part of the recovery process. Failure to replace all of the fluid loss has been termed voluntary dehydration. When looking at fluid replacement, it's important to assess and understand what drives drinking behaviours in order to help prevent dehydration from occurring at a severe level, and also from preventing overhydration from occurring. Two main fluid intake mechanisms have been reported looking at sensations of thirst, desire to drink, and the subsequent impact on fluid intake. These are hyperosmolality and also hypovolemia. And these result in an increase in vasopressin release and aldosterone release, respectively. Focusing on hyperosmolality, following exercise and dehydration occurs, osmolality tends to increase. It's caused by increase in cell tonicity. However, it's been shown in the literature that an increase in blood lactate concentration can also increase serum osmolality through an increase in serum sodium levels. So when looking at an exercise such as high-intensity intermittent exercise, there is often an increase in blood lactate concentration. However, the exercise does not always result in dehydration levels that may result in high osmolality levels through dehydration. And therefore, we're looking at the increase in osmolality following an increase in lactate concentration on subsequent fluid intake and fluid intake behaviour. So looking at the proposed mechanism of this high-intensity intermittent exercise and its impact on potential impact on fluid intake. Following exercise, there is often an increase in blood lactate concentration, which in turn decreases sodium release from the vascular space. This can have an impact on increasing serum osmolality, which has been shown to increase sensations of thirst and also arginine vasopressin release. These two, in turn, potentially could impact on fluid intake and potentially increase fluid intake. So therefore, the aim of the study was to examine the effect of high-intensity intermittent exercise on voluntary fluid intake and markers of hydration. So 10 healthy male subjects were recruited from the local area. Their subjective characteristics are displayed here. They're all recreationally active participants. They're asked to visit the lab on 4 occasions, once for a VO2 peak test on a cyclogometer, once for thermalisation, and twice more for experimental trials. The experimental trials were identical, except for the difference in the exercise protocol performed. The difference in the exercise was each exercise period consisted of 60 minutes. In the high-intensity trial, it was 2 minutes rest, followed by 1 minute at the power output achieved to elicit VO2 peak during the VO2 peak test, and this was repeated 20 times. So there was 20 minutes of 20 times 1 minute hard exercise. In the continuous or low-intensity trial, there was 60 minutes of 33% of the power output generated from the VO2 peak test, and this was performed continuously for 60 minutes. This schematic shows the outline of the time spent in the lab. The dashed arrow represents the point at which urine and body mass samples were taken. The red arrows represent when blood samples were taken, and the blue arrows represent the point at which fluid intake was measured. So subjects arrived in the lab in a fasted state 2 hours after consuming 500 millilitres of water. This was to ensure a standardised state of euhydration. They came into the lab, and there were 3 periods: a rest or baseline period, the exercise period, and the recovery period. In the rest period, subjects sat for 30 minutes after a body mass weight and urine sample. So they sat for 30 minutes, and a cannula was inserted to allow repeated blood sampling. After 30 minutes, a blood sample was taken, and then subjects exercised in one of the 2 protocols. Following completion of exercise, a further blood sample was taken, and then subjects were seated for an hour during the recovery period, where blood samples were taken at 5, 15, 30 and 60 minutes of the recovery period. During this recovery period, fluid intake, free access to fluid in the form of tap water was allowed. This was measured, but the subjects did not know about the measuring of the fluid. So look at some of the preliminary results we've got. This first slide shows fluid intake during both trials during the recovery period. I split the recovery period into two 30-minute periods, so between 0 and 30 and 30 and 60 minutes, and then the total shown on the far right-hand side. The high-intensity trials in red and the continuous low-intensity in blue. There was a significant difference in fluid intake during the first 30 minutes between trials, and this was about 350 ml compared to about 200 ml between the two trials. And this largely accounted for the significant difference in total fluid intake over the recovery period. Fluid intake during the second 30-minute period, so between 30 and 60, was similar between trials and was significantly less than compared to the first 30 minutes in both trials. Taking into account fluid intake, sweat losses and urine output, changes in body mass from baseline were similar between the two trials and were about 1%. So in the high-intensity trial, there was an increase in fluid intake, but this was offset by increased sweat losses during the exercise period, resulting in similar changes in body mass. Urine output was the same, similar in both conditions. We move on to the blood markers, so looking at the proposed mechanism from earlier. The figure on the left shows blood lactate concentration, again with the continuous low-intensity trial in blue and the high-intensity trial in red. You can see that in the continuous trial, there was no change in blood lactate concentration above baseline measures. In the high-intensity trial, there was a peak in blood lactate concentration at post-exercise, and this gradually decreased from that peak at post-exercise and returned to baseline by 60 minutes. There is a significant difference between trials in blood lactate at post-exercise and in 5, 15, 30 and 60 minutes of the recovery period. Looking at how blood lactate may influence serum sodium concentration, you can see a sodium concentration on the right-hand side, you can see a similar trend with a peak at post-exercise in the high-intensity trial. However, this then decreased down back to baseline values after 5 minutes, so following the onset of drinking. In the continuous trial, there was no change above baseline, and there was a significant difference between trials at post-exercise values. The relationship or correlation between lactate concentration and serum sodium concentration was an R value of 0.608, so relatively strong. If we then look at how serum sodium concentration can then has impacted on serum osmolality, as shown by the figure on the left, again it's a similar trend with a peak value of serum osmolality occurring at post-exercise in the high-intensity trial, and then decreasing following the onset of fluid intake back down towards baseline values during the blood samples taken in the recovery period. Again, in the continuous trial, there was no change above baseline. However, in the serum osmolality, there was, unlike the serum sodium, where there was only a difference between trials at post-exercise, there was a difference between trials at post-exercise after 5 minutes and also after 30 minutes. Despite significant differences in post-exercise values of blood lactate, serum osmolality and serum sodium, thirst, as shown on the right, sensations of thirst, was not significantly different post-exercise. However, there was a tendency for it to be greater, sensations of thirst to be greater in the high-intensity trial at post-exercise with a p-value of 0.06. Again, similar to the previous measures, the peak occurred at post-exercise and in the high-intensity trial and decreased back towards baseline values during the rest of the recovery period. Similar to the other measures, continuous trial, sensations of thirst were similar to baseline values. The correlation between serum osmolality and thirst was 0.419 and significant again. So that's most of the analysis I've completed so far. The remaining analysis is going to look at the hormone data, so looking at vasopressin and aldosterone responses and see if they match up with osmolality values and serum sodium values. Conclusion so far, there appears to be a higher serum osmolality and fluid intake following high-intensity intermittent exercise, and this is probably attributed to the increase in lactate concentration affecting serum sodium levels. Future plans from this study is to expand on the findings and assess osmolality and lactate responses when following high-intensity exercise, when there is a delay in fluid or there is no fluid prescribed, to see if the osmolality values decrease and lactate values are influenced depending on the fluid and when it is prescribed. So thank you for listening.